In 2019, a team of physicists in Edinburgh ran an experiment that should have broken the news cycle. They set up a test involving 6 photons, 3 entangled pairs, a carefully calibrated laser, and a question that had haunted quantum mechanics for nearly 60 years. When the data came back, it confirmed something that most physicists had hoped would never be confirmed. 2 observers had measured the same quantum system. They got different results, and both results were correct. Not because one of them made an error, not because they were looking at different aspects of the same event, not because quantum mechanics is fuzzy or probabilistic in the way pop science usually describes. Both results were correct because both realities were real. The experiment did not show that one observer was wrong and the other was right. It showed that the idea of a single reality, one objective truth that all observers share, is not a feature of the universe. It is an assumption, and that assumption, as of 2019, has been experimentally falsified. The paper was published in Science Advances, one of the most prestigious peer-reviewed journals in the world. The result cleared 5 standard deviations, the same statistical threshold that CERN required before announcing the discovery of the Higgs boson. This was not a fringe claim. This was not speculative philosophy dressed up as physics. This was data. And the data said something that should have changed how you think about every conversation you have ever had, every shared experience you believe you have had with another person, every assumption you have ever made about the world being one world that we all inhabit together. What happened in that lab in Edinburgh might mean that the reality you wake up in every morning is not the same reality as the one experienced by the person sleeping next to you. And it never has been. The man who first asked the question that led to this experiment was a Hungarian physicist named Eugene Wigner. And to understand why his question cut so deep, you need to understand the world that produced him. Wigner was born on November 17, 1902, in Budapest, into a middle-class Jewish family. His father Antal managed a leather tanning factory. His mother Erzsébet came from the Einhorn family, a name that meant something in the business circles of the Austro-Hungarian Empire. The family was comfortable but not wealthy. They were assimilated, secular, part of a generation of Hungarian Jews who believed that education and professional achievement were the path to belonging. They were right about the education part. They were tragically wrong about the belonging. The school that shaped Wigner was the Fasori Evangelikas Gymnasium, widely considered the finest secondary school in Hungary and possibly in all of Central Europe. The building still stands in Budapest, a Lutheran institution that accepted students regardless of religion during an era when such tolerance was not universal. What made Fasori extraordinary was not the building or the curriculum, but a single mathematician named Laszlo Ratz. Ratz was not a famous mathematician. He published no important theorems. He held no university chair. What he had was an almost supernatural ability to recognize talent and nurture it. He would identify promising students and meet with them individually, guiding them through problems far beyond the standard curriculum, treating them as colleagues rather than children. Decades later, when Eugene Wigner stood in Stockholm to accept the Nobel Prize in physics, he devoted a significant portion of his acceptance speech to Ratz. He called him the greatest influence on his intellectual development. For a man who had worked alongside Einstein, Fermi, and Bohr, that was not a small statement. But here is the detail that makes you understand just how concentrated the talent at Fasori was. Sitting 1 year behind Wigner, in the same school, studying under the same Laszlo Ratz, was another student named János von Neumann. You probably know him as John von Neumann, the mathematician who would go on to help invent the modern computer, design the architecture that still powers the device you are using to hear this, create game theory, contribute foundationally to quantum mechanics, work on the Manhattan Project, and generally be regarded as one of the 2 or 3 most intelligent human beings of the 20th century. Wigner and von Neumann met as teenagers in Budapest. They remained friends and intellectual sparring partners for the rest of their lives. When people asked Wigner about the Hungarian phenomenon, about why so many extraordinary scientists emerged from such a small country in such a short period, he had a standard deflection. He would say that von Neumann was the only genius. He would say that von Neumann was a much better mathematician than he was, and a better scientist. But then he would add, almost as an afterthought, that he knew more physics. Coming from Wigner, this was not modesty, it was precision. Wigner's father did not want him to become a physicist. The question Antal Wigner asked his son has echoed through the history of science. Just how many physicists do you really think Hungary needs today? It was a practical question from a practical man. Antal wanted his son to study something useful, something that would lead to a secure career. Chemical engineering, that was the compromise. Eugene would get his technical education, and if he wanted to dabble in theoretical physics on the side, that was his business. So Wigner enrolled at the Technische Hochschule in Berlin, dutifully studying chemical engineering while his mind wandered toward the questions he actually cared about. The compromise turned out to be no compromise at all. Berlin in the 1920s was the center of the physics universe. The Wednesday colloquia of the German Physical Society brought together Einstein, Planck, Heisenberg, Schrödinger, and Pauli. Wigner attended these colloquia whenever he could. He sat in the back and listened to the people who were reinventing how humanity understood reality. The tannery began to feel very far away. He earned his doctorate in 1925, a thesis on chemical reaction rates that nobody remembers today. Then he did something that sounds like a tragedy, but was really just a delay. He went home. His father needed him at the tannery. For an entire year, the man who would win the Nobel Prize for his contributions to nuclear physics worked in leather processing. He later described this period simply, "I did not feel that this was my life." The rescue came in the form of an invitation to assist with X-ray crystallography research back in Berlin. Wigner took it. He never worked in his father's tannery again. Within a few years, he had made his name in quantum mechanics, publishing papers on symmetry principles that would eventually form the backbone of modern particle physics. By 1930, Princeton University had recruited both Wigner and von Neumann, offering them salaries 7 times what they could earn in Europe. America wanted the Hungarian geniuses, and America was willing to pay. The timing was fortunate. When the Nazis came to power in 1933, they removed Wigner from his position in Berlin. The official reason was his Jewish ancestry. Wigner was already in Princeton by then, already an American physicist in all but paperwork. He became a citizen in 1937, but the pattern of his life, the rhythm of brilliance interrupted by loss, was already established. In 1936, Princeton declined to renew his contract. They never explained why. Wigner found a position at the University of Wisconsin, but he carried the rejection with him. "I could not help feeling angry," he said later. For a man as measured and polite as Wigner, this was an unusual admission. At Wisconsin, he met a physics student named Amelia Frank. They married. For the first time in years, Wigner seemed happy. The marriage lasted less than a year. On August 16, 1937, Amelia died unexpectedly. The details have been lost to history, or perhaps Wigner simply never spoke of them. What remains is the fact. He was 34 years old, his wife was gone, Princeton had rejected him. The country of his birth was sliding toward catastrophe, and the questions that consumed him, the questions about the nature of reality and measurement, and what it meant for something to be observed, those questions were no closer to being answered. Princeton invited him back in 1938. He accepted. He remarried eventually to another physicist named Mary Wheeler, and the marriage lasted. In one of those coincidences that sounds invented, but actually happened, Wigner introduced his younger sister Margit to the physicist Paul Dirac during a visit to Princeton. Margit and Dirac married in 1937. For the rest of his life, Wigner delighted in referring to Dirac, one of the most important physicists of the 20th century, as my famous brother-in-law. Then came the war. Wigner's background in chemical engineering, the practical education his father had insisted upon, turned out to be exactly what the Manhattan Project needed. The theoretical physicists could design bombs, but someone had to figure out how to actually produce the plutonium. Wigner led the team at the University of Chicago's metallurgical laboratory that designed the Hanford plutonium production reactors. These were engineering challenges on a scale that had never been attempted. They succeeded. On December 2nd, 1942, Wigner was present when Chicago Pile 1 achieved the first self-sustaining nuclear chain reaction. He had brought a bottle of Chianti to celebrate. The wine was consumed in paper cups. No one made a toast. There was nothing to say that matched the weight of what had just happened. Unlike Einstein, Wigner never expressed regret about his role in developing nuclear weapons. He was only sorry, he said, that the bomb had not been ready earlier. Coming from a Hungarian Jew who had watched the Nazis rise to power, who had lost colleagues and relatives to the Holocaust, this was not callousness. It was clarity. He knew what the alternative had been. The Nobel Prize came in 1963 for his contributions to the theory of the atomic nucleus and the elementary particles, particularly through the discovery and application of fundamental symmetry principles. By then, Wigner was 60 years old, a distinguished professor, a member of every important scientific academy, a man who had shaped the 20th century in ways that most people would never understand, and he was still thinking about a problem that had nagged at him for decades. A problem about observation and reality, and what happens when one person looks at a quantum system while another person looks at them looking. The essay where Wigner first laid out this problem appeared in 1961 in a book with the wonderful title, The Scientist Speculates. The subtitle was even better, An Anthology of Partly Baked Ideas. This was not false modesty. The collection was exactly what it claimed to be, a gathering of speculative essays from scientists willing to venture beyond what they could prove. Wigner's contribution was called Remarks on the Mind-Body Question. It was later reprinted in the landmark collection Quantum Theory and Measurement, edited by John Wheeler and Wojciech Zurek, where it became one of the most cited papers in the foundations of physics. The thought experiment Wigner proposed is deceptively simple. You need only three things to understand it: a quantum system in superposition, an observer who measures that system, and another observer who watches the first observer. Here is the setup. A photon exists in a superposition of two states. For simplicity, call them flash and no flash, though the actual physics involves polarization. Wigner's friend, a colleague sealed inside a laboratory, measures the photon. The friend looks at a detector and sees a definite result. Either the detector flashed or it did not. From the friend's perspective, the superposition has collapsed. The photon is now in one state or the other. The friend knows which state because the friend looked at it. But Wigner is standing outside the sealed laboratory. He has not looked at the detector. He has not asked his friend what happened. According to quantum mechanics, Wigner must describe the situation differently. For Wigner, the photon has not collapsed into a definite state. The entire system, the photon plus the detector, plus the friend, is now in an entangled superposition. The friend is simultaneously in a state of having seen a flash and having seen no flash. Not metaphorically. According to the math, the friend is in a genuine quantum superposition, just like the photon was before anyone looked at it. Now Wigner opens the laboratory and asks his friend what happened. The friend reports seeing a definite result. The friend says, quite confidently, that the detector flashed, or that it did not flash. The friend experienced no ambiguity. From the friend's perspective, there was always a fact of the matter, but according to Wigner's description, there was no fact of the matter until Wigner himself learned the answer. The friend was in superposition. The friend only became a person who had seen a definite flash when Wigner's consciousness registered the information. When did collapse actually happen? When the friend looked at the detector? Or when Wigner learned what the friend saw, the friend would say collapse happened at the moment of measurement, inside the laboratory, before Wigner knew anything. Wigner's quantum description would say collapse happened later, when the information reached Wigner's mind. Both cannot be right. But quantum mechanics does not tell you which one is wrong. This is different from Schrödinger's cat, though it is easy to confuse them. Schrödinger proposed his cat in 1935 as a way of attacking the Copenhagen interpretation. A cat is placed in a box with the radioactive atom and a vial of poison. If the atom decays, the poison is released and the cat dies. According to the Copenhagen interpretation, the atom is in superposition until someone observes it. Therefore, the cat is in superposition too, alive and dead at the same time. Schrödinger meant this as a reductio ad absurdum. He was saying, look how ridiculous this interpretation is when you scale it up. A cat cannot be alive and dead at the same time. That is absurd. Therefore, the interpretation must be wrong somewhere. But here is what most popular science presentations get wrong about Schrödinger's cat. Schrödinger was not celebrating quantum weirdness. He was not saying, isn't it amazing that cats can be alive and dead? He was attacking the theory. He was saying this consequence is so ridiculous that we need to rethink our assumptions. The fact that his thought experiment is now used as an example of how cool and counterintuitive quantum mechanics is would have horrified him. He was pointing at a flaw. Pop science turned it into a feature. Wigner's friend is different because a cat cannot report its experience. A cat cannot say, I remember being in a definite state the whole time. A cat cannot look Wigner in the eye and insist that there was always a fact of the matter about whether it was alive. But a human friend can. A human friend has consciousness, memory, the ability to reflect on their own experience. When the friend tells Wigner, I saw a definite flash the whole time, Wigner has to take that report seriously. The friend's memory says collapse happened at one time. Wigner's quantum mechanics says collapse happened at a different time. The friend and the formalism directly contradict each other. Wigner's original resolution to this paradox was radical. He proposed that consciousness is special. Consciousness is not just another physical process that can be described by quantum mechanics. Consciousness is what causes wave function collapse. When the friend, a conscious being, looks at the detector, that is when the superposition collapses. The friend's mind does something that a detector alone cannot do. This was a serious proposal from a serious physicist. Wigner was not drifting into mysticism. He was following the logic of quantum mechanics to what he saw as its inevitable conclusion. If you take the formalism seriously, if you do not artificially exempt macroscopic objects from quantum description, then at some point you have to explain why we never see superpositions. Wigner's answer was that consciousness is the explanation. It follows that the being with consciousness must have a different role in quantum mechanics than the inanimate measuring device. For about 2 decades, this was Wigner's position. Consciousness was the missing piece that completed quantum mechanics. The mind was not just a passive observer of reality. The mind was what made reality definite. Then he changed his mind. In the 1980s, influenced by H. Dieter Zer's work on decoherence, Wigner came to see his earlier position as untenable. He called it solipsism. He came to regard the paradox of his friend not as evidence that consciousness is special, but as evidence that quantum mechanics itself needed revision. Something was wrong with the theory. The measurement problem was a genuine problem, not a mystery to be resolved by invoking the mind. But Wigner never accepted the main alternative on offer. The many worlds interpretation proposed by Hugh Everett in 1957 said that there was no collapse at all. Every time a measurement occurred, the universe branched. In one branch, the friend saw a flash. In another branch, the friend saw no flash. Both branches were equally real. The appearance of collapse was just the result of being in one branch and not having access to the others. Wigner dismissed this. He called the notion of a state function of the universe senseless. Until his death in 1995, he maintained that quantum mechanics was incomplete, that the measurement problem was real, and that no existing interpretation adequately resolved the paradox he had identified in 1961. The question he asked had no clean answer. When does collapse happen? Where does quantum description end and classical reality begin? What makes measurement special? For 60 years after Wigner's essay, these questions remained philosophy. Interesting philosophy. Important philosophy. But philosophy nonetheless. You could debate them forever because there was no experiment that could distinguish between the answers. And that is where the story should have stayed. A famous thought experiment, a paradox that illuminated the conceptual foundations of physics, a puzzle for philosophers and a nuisance for physicists who preferred to shut up and calculate. But physics has a way of turning philosophy into data. And in 2018, two separate teams of theorists figured out how to turn Wigner's question into an experiment. The problem that Wigner identified in 1961 is sometimes called the measurement problem, but that name undersells it. It is not a problem in the sense of a puzzle that smart people are working on and will eventually solve. It is a crack in the foundations of all empirical science. And the crack has been there since the beginning. Here is what quantum mechanics actually says. A physical system, let us say an electron, does not have definite properties until it is measured. Before measurement, the electron exists in a superposition of all possible states. It is not that we do not know where the electron is. The electron genuinely does not have a location. It is not anywhere. It is in a mathematical ghost state that includes all possible locations at once. When you measure the electron, the superposition collapses. The electron is now here, at this specific location, with this specific momentum. The act of measurement transforms the mathematical ghost into a physical object with definite properties. This is called wave function collapse, and it is the central event in quantum mechanics. The Copenhagen interpretation, the version of quantum mechanics that most physicists learn and use, treats collapse as primitive. It does not explain collapse. It does not describe the mechanism of collapse. It simply says that when a measurement happens, collapse happens. A wave function, which describes the superposition, is replaced by a new wave function that describes the definite result. What counts as a measurement? The Copenhagen interpretation does not say. Niels Bohr, who developed the interpretation with Werner Heisenberg in the 1920s, drew a line between the quantum world and the classical world. He called it the Heisenberg cut. Below the cut, quantum mechanics applies. Superpositions exist. Particles do not have definite properties. Above the cut, classical physics applies. Objects have locations. Measurements have results. The cut is where quantum becomes classical. But where is the cut? Bohr never said precisely. He could not say precisely because there is no principled way to draw the line. Is an atom below the cut or above it? What about a molecule? What about a virus? What about a cat? What about a human brain? The standard answer is that the cut is a matter of practical convenience. You draw it wherever it is useful to draw it. If you are doing an experiment on a single electron, you draw the cut between the electron and your detector. The electron is quantum. The detector is classical. You do not need to treat the detector as a quantum system because it is big enough that quantum effects wash out. This answer works fine for calculations. It does not work at all for understanding what is actually happening. If quantum mechanics is a true description of reality, then the detector is also made of quantum systems. The atoms in the detector are in superposition. The electrons in the detector are in superposition. At what point do all these individual superpositions combine to produce a classical object with a definite state? Decoherence, developed in the 1970s and 80s, provides part of the answer. When a quantum system interacts with its environment, the different branches of its superposition become entangled with different states of the environment. This entanglement effectively destroys the interference between branches. The system behaves as if it is in a classical mixture of states, rather than a quantum superposition of states. Decoherence is real. It has been measured. It explains why quantum effects are hard to observe at macroscopic scales. The environment is constantly interacting with large objects, constantly entangling with them, constantly destroying the delicate coherence that allows superpositions to manifest. But decoherence does not solve the measurement problem. Decoherence explains why we do not see interference between branches. It does not explain why we see one branch rather than another. After decoherence, the system is in a classical mixture. It is either in state A or in state B, with certain probabilities. But the theory does not say which one. The theory does not produce a definite outcome. It produces probabilities of outcomes. When you look at the detector and see that the electron is here, something has happened that decoherence does not describe. You have obtained a definite result, not a probability, not a mixture, a fact. The electron is here, not there. Decoherence cannot explain how facts emerge from probabilities. This is the measurement problem. Quantum mechanics is the most precisely tested theory in the history of science. It predicts the outcomes of experiments to 11 decimal places of accuracy. It underlies all of chemistry, all of electronics, all of modern technology. And it does not explain how measurement results become definite. You might think this is a technical problem that only bothers philosophers. You would be wrong. The measurement problem is not about quantum mechanics being weird. It is about quantum mechanics being incomplete. The theory does not describe the process by which the world becomes the world. It describes probabilities. Something else has to convert those probabilities into actualities. The theory does not say what that something is. For most of the 20th century, physicists dealt with this by not dealing with it. The Copenhagen interpretation's unofficial motto was "shut up and calculate." The formalism works. Use the formalism. Do not ask what it means. Bohr himself was suspicious of questions about reality. He seemed to regard them as somehow illegitimate, as though asking what quantum mechanics meant was a category error. This worked for a while. Quantum mechanics was producing answers that matched experiments. The technology was advancing. Nobody needed to resolve the measurement problem to build a transistor. But the problem did not go away. It was always there, underneath. And every time experimentalists pushed quantum effects to larger scales, the problem became harder to ignore. In 1990, a team in Vienna demonstrated interference with molecules of 60 carbon atoms, buckyballs, objects large enough to see under a microscope. They passed through a double slit and produced an interference pattern, just like photons, just like electrons. The molecules were in superposition. In 2019, a different team in Vienna demonstrated interference with molecules of over 800 atoms, the heaviest and most complex objects ever shown to exhibit quantum behavior. If molecules of 800 atoms can be in superposition, where does superposition end? The cut keeps moving. Every time someone tests whether quantum effects persist at larger scales, they persist. There is no evidence for a boundary between quantum and classical. There is no evidence that large objects are exempt from superposition. The only reason we do not see superpositions in everyday life is decoherence, and decoherence does not make superpositions go away. It just hides them. So where does this leave Wigner's friend? The friend is a human being. The friend has a brain made of neurons, made of molecules, made of atoms, made of electrons. At every level, the friend is a quantum system. If molecules of 800 atoms can be in superposition, why not neurons? If neurons, why not brains? If brains, why not the conscious experience that emerges from brains? It draws the cut somewhere, anywhere, wherever is convenient. But the cut is arbitrary. The cut has no physical justification. The cut is a choice made by the physicist, not a feature of nature. Wigner saw this. His thought experiment was designed to push the cut to its breaking point. If the friend is below the cut, then the friend is in superposition until Wigner looks. If the friend is above the cut, then the friend has a definite experience before Wigner looks. But quantum mechanics does not tell you where the cut is. It does not even tell you that there is a cut. The cut is imposed from outside the theory. This is what makes the measurement problem so deep. It is not a gap in our knowledge. It is a gap in the theory. Quantum mechanics describes evolution of superpositions. It does not describe collapse of superpositions. Collapse is added by hand, imposed as an additional postulate, never derived from anything more fundamental. Every interpretation of quantum mechanics is really an attempt to fill this gap. Copenhagen fills it by refusing to answer, treating measurement as primitive, and telling you not to ask questions. Many worlds fills it by denying that collapse happens, treating all branches as equally real. Pilot wave theory fills it by denying that superpositions are fundamental, treating particles as always having definite positions guided by a wave. Objective collapse theories fill it by modifying the equations, adding new terms that cause superpositions to spontaneously collapse at large scales. None of these interpretations can be distinguished by any experiment that had been performed by 2017. They all make the same predictions for every test that had ever been conducted. The choice between them was a matter of philosophy, aesthetics, personal preference, not physics. And that is what changed in 2018. Two separate groups of theorists realized that Wigner's friend could be turned into an experiment. Not an experiment that would test quantum mechanics itself. Quantum mechanics was not in question. An experiment that would test the assumptions that underlie any interpretation. An experiment that would force physics to give something up. The first breakthrough came from Daniela Frautschiger and Renato Renner at ETH Zurich. Their paper had been circulating since April 2016, posted to the arXiv preprint server under a title that sounded almost confrontational. Quantum theory cannot consistently describe the use of itself. For 2 years, the paper generated fierce debate. Physicists argued about whether the reasoning was valid, whether the assumptions were fair, whether the conclusion was really as radical as it seemed. In September 2018, the paper was finally published in Nature Communications. The debate had not been settled. The paper was published because the editors recognized that the argument deserved to be taken seriously. Frautschiger and Renner constructed a thought experiment involving 4 agents. 2 of them, call them Alice's friend and Bob's friend, perform measurements on quantum systems. 2 of them, Alice and Bob, reason about what the friends measured. All 4 agents apply quantum mechanics to model each other. They use the theory to make predictions about what the other agents will see. The result is a contradiction, not a paradox that can be dissolved by careful analysis. A logical contradiction. Agent Alice's reasoning leads her to be certain that a particular result is heads. Agent Bob's reasoning leads him to be certain that the same result is tails. Both agents are applying quantum mechanics correctly. Both agents are reasoning validly. And they reach conclusions that cannot both be true. Frauchiger and Renner identified three assumptions that lead to this contradiction. The first assumption is that quantum mechanics is universally valid. It applies to all systems, including systems that contain observers. The second assumption is that reasoning is consistent. If an agent uses valid logic to derive a conclusion, other agents should accept that conclusion. The third assumption is that measurements have single outcomes. When you measure a system, you get one result, not many. These three assumptions cannot all be true. At least one of them must fail. Frauchiger and Renner did not say which one. They left that as a choice for the reader, but they proved that you cannot have all three. The consistent application of quantum mechanics to observers produces contradictions. Renato Renner later described the reactions to this result. He said some of his colleagues responded very emotionally. This was not a polite way of saying his colleagues disagreed. It was a polite way of saying his colleagues were upset. The foundations of physics are supposed to be stable. You can build quantum computers on top of them. You can trust the predictions. You do not expect a paper to come along and say, by the way, your fundamental theory cannot consistently describe situations where people use the theory to reason about each other. The second breakthrough came from Czeslaw Bruckner at the University of Vienna. Bruckner had been working on Wigner's friend for years, publishing preliminary results in 2015 and refining them over time. In 2018, he published a paper showing how to turn the extended Wigner's friend scenario into a Bell-type test. Bell tests are among the most important experiments in physics. John Bell proved in 1964 that any theory satisfying certain reasonable assumptions must obey certain inequalities. If you measure correlations between entangled particles, the correlations cannot exceed a specific bound. When Alain Aspect performed the first rigorous Bell test in 1982, he found that quantum mechanics violated Bell's inequalities. The correlations were stronger than any local realistic theory could explain. This result, replicated hundreds of times with increasing precision, was recognized with the 2022 Nobel Prize in Physics. Bruckner realized that you could construct something similar for Wigner's friend. Instead of testing local realism, you could test what he called local observer independence. The setup would involve two friends and two Wigners sharing an entangled quantum state. The friends would measure the quantum systems. The Wigners would choose whether to simply ask the friends what they saw, or to perform a more complex interference measurement on the entire friend plus system composite. By analyzing the correlations between all these measurements, you could derive an inequality. Call it a Bell-Wigner inequality. If the inequality is satisfied, then three assumptions are all true simultaneously. If the inequality is violated, then at least one of the three assumptions must be false. The three assumptions in Bruckner's framework are slightly different from Frauchiger and Renner's, but they aim at the same target. The first assumption is locality. Alice's choice of measurement cannot influence Bob's result, and vice versa. No superluminal signaling, no action at a distance. This is the same assumption that Bell tested, and it is preserved in quantum mechanics. The second assumption is freedom of choice. The measurement settings that Alice and Bob select are free variables. They are not predetermined by the prior state of the universe. This rules out superdeterminism, the idea that everything, including your choice of experiments, was fixed at the Big Bang. The third assumption is observer-independent facts. When a friend measures a quantum system and sees a result, that result is a fact of the world. It is not just a fact for the friend, it is an objective fact that any observer could in principle access and agree upon. These three assumptions are what most scientists would consider the minimal requirements for doing science at all. Locality says you cannot influence distant events instantaneously. Freedom of choice says experiments are not predetermined. Observer-independent facts says that measurements reveal objective truths about the world. Bruckner's inequality holds if all three assumptions are true, Quantum mechanics predicts that the inequality is violated. This is not like a standard Bell test. In a standard Bell test, the violation forces you to give up local realism, the idea that particles have predetermined values independent of measurement. That is strange, but physicists have had decades to get used to it. In a Bell-Wigner test, the violation forces you to give up something different. If you want to keep locality and freedom of choice, you have to give up observer-independent facts. Let that settle for a moment. The assumption under threat is not some obscure technical condition. It is the assumption that when you measure something and get a result, that result is objectively true, that someone else measuring the same thing would get the same result, that there is a fact of the matter about what happened, independent of who is asking. If observer-independent facts is false, then different observers can have different facts about the same event, not different interpretations, not different perspectives, different facts, both correct, both real, and no higher authority that can say which one is the true fact. There are only facts relative to observers. This is what Bruckner's framework made testable. For the first time, there was a way to experimentally probe whether observer-independent facts exist. The theory said they do not. The experiment would check whether the theory was right. In Edinburgh, a PhD student named Massimiliano Proietti read Bruckner's paper and saw an opportunity. Proietti was working in the Edinburgh mostly quantum lab led by Alessandro Fedrizzi at Heriot-Watt University. The lab specialized in photonic experiments, using light to test fundamental questions about quantum mechanics. They had the equipment, they had the expertise, they had a theoretical prediction waiting to be tested. The experiment would require 6 photons, 3 entangled pairs, generated simultaneously, manipulated precisely, measured in careful coordination. 6-photon coincidence events are rare. Even with a powerful laser and optimized optics, you might wait hours between usable data points. The statistics would take weeks to accumulate, but it was possible. Barely possible, but possible. Proietti began building the apparatus. The technical challenges were formidable. You cannot put a human friend in superposition. The decoherence time for a human brain is estimated at around 10 to the negative 20 seconds. In that time, a photon would travel a distance smaller than an atom. For any practical purpose, human brains decohere instantly. Whatever superposition exists is destroyed before you could ever hope to measure it. But Bruckner's theoretical framework did not require human friends. What it required was systems that could record and store measurement results, systems that could be placed in superposition, systems that could be measured in different ways depending on the choice of the external observer. The friends did not need to be conscious. They needed to be quantum mechanical record keepers. Photons could do this. The polarization of a photon is a 2-state quantum system. Like the spin of an electron or the energy levels of an atom, you can prepare a photon in a superposition of horizontal and vertical polarization. You can measure it and get a definite result. You can entangle it with other photons so that their polarizations are correlated. In Proietti's experiment, photons would play all the roles. One pair of entangled photons would serve as the quantum coins, the systems being measured by the friends. Additional photons would serve as the friends themselves, their polarization states acting as records of what the friends observed. The Wigners would be represented by the measurement choices made at the end of the optical circuit, either reading the friend's record directly or performing an interference measurement that treated the friend as still being in superposition. This was not a cheat. This was the entire point. If observer-independent facts exist, it should not matter that the friends are photons rather than humans. A fact is a fact. A measurement result is a measurement result. The size or complexity of the observer should be irrelevant. If you believe that observer-independent facts exist, you should believe that photon friends are entitled to their facts just as much as human friends. If you do not believe this, if you think there is something special about human observers that makes their facts more real than photon facts, then you need to say what that something is. You need to explain where the boundary lies. You need to provide a principled reason why photons do not count. And as we have already seen, nobody has ever provided such a reason. The Heisenberg cut has no theoretical justification. It is drawn wherever convenient. The experiment used a 775 nanometer pulsed titanium sapphire laser focused into periodically poled potassium titanyl phosphate crystals. When photons from this laser pass through these crystals, a process called type 2 spontaneous parametric down conversion occasionally produces pairs of entangled photons. The photons emerge with their polarizations correlated in a specific way. If you measure one and find it horizontally polarized, the other will be vertically polarized. And vice versa, they are born entangled. 3 such sources produced 3 entangled pairs simultaneously. This requires extraordinary timing. The laser pulses had to be precisely synchronized, the optical paths had to be matched to within a fraction of a wavelength. Any mismatch would destroy the coherence that made the experiment possible. One pair of entangled photons served as the central quantum system, the coins being shared between the 2 laboratories. Call them the system photons. 2 more pairs provided the ancillary photons, 1 pair for each laboratory. In each lab, 1 photon from the ancillary pair would serve as the friend, recording the result of a measurement on the system photon. The other photon from the ancillary pair would be sent to the corresponding Wigner for measurement. The key element was the optical fusion gate. This is a quantum circuit based on the Brown-Rudolph scheme, a technique for entangling photons using only linear optics and post-selection. When the system photon and the friend photon pass through the fusion gate, they become entangled. The polarization of the friend photon now encodes information about the system photon. The friend has measured the coin, but here is the crucial subtlety. The friend has measured the coin while remaining in superposition. The fusion gate entangles the photons without collapsing either of them. From the friend's perspective, if the friend could have a perspective, the measurement has happened. The friend's polarization now correlates with the coin's polarization. But from outside the laboratory, the entire system, the coin plus the friend, remains in a coherent superposition. This is exactly the situation Wigner described in 1961. The friend has a definite experience. The external observer describes the friend as not having a definite experience. The experiment instantiates the thought experiment in actual hardware. Each Wigner, Alice, and Bob could choose between 2 measurement settings. Setting 0 meant open the laboratory. Read what the friend observed. Measure the friend photon in the computational basis, the basis that corresponds to the friend's recorded result. This is what you would do if you wanted to know what the friend saw. It treats the friend's measurement as having produced a definite fact. Setting 1 meant perform a Wigner-type measurement. Do not read the friend's record. Instead, measure the entire friend plus system composite in a basis that reveals whether the composite is in superposition. This is an interference measurement, analogous to the measurements that reveal quantum coherence in double-slit experiments. It treats the friend as not having produced a definite fact, as still being in superposition along with the quantum system. The Bell-Wigner inequality involves correlations across all 4 combinations of measurement settings. Alice chooses 0 or 1. Bob chooses 0 or 1. For each combination, the experiment measures correlations between the results. If the 3 assumptions, locality, freedom of choice, and observer-independent facts, are all true, then a particular combination of these correlations, the Bell-Wigner parameter S, must be less than or equal to 2. Quantum mechanics predicts that S can be as large as 2 times the square root of 2, approximately 2.83. This is the same maximum as the standard CHSH-Bell inequality. The math is structurally identical. The interpretation is completely different. Data collection took weeks. 6 photon coincidence events are extremely rare. Even with careful optimization of the photon sources and detectors, usable events occurred only a handful of times per hour. The pump power was held to 100 milliwatts, far below the maximum the laser could provide, specifically to suppress multi-pair noise. At higher powers, the sources would occasionally produce 4 photons instead of 2, contaminating the data with spurious coincidences. This is the tedium of experimental physics that popular accounts rarely mention. The theory is exciting, the apparatus is painstaking. Hours of alignment, calibration, troubleshooting. Days of data collection. Systematic checks for every possible source of error. The glamour of fundamental physics is built on a foundation of meticulous, boring, repetitive work. When the data was finally sufficient, when the error bars were small enough to draw a conclusion, Proietti and his collaborators computed the Bell-Wigner parameter, S. The result was 5 standard deviations above 2. In physics, 5 standard deviations is the threshold for claiming a discovery. It corresponds to a probability of roughly 1 in 3.5 million that the result occurred by chance. The Higgs boson was announced at 5 sigma. Gravitational waves were announced at 5 sigma. This is not a marginal result. This is not suggestive evidence. This is the standard of proof that physics requires before declaring something real. The Bell-Wigner inequality was violated. The 3 assumptions, locality, freedom of choice, and observer-independent facts, cannot all be true. The paper was published in Science Advances on September 20, 2019. The author list included Massimiliano Proietti, Alexander Pixton, Francesco Graffiti, Peter Barrow, Dimitro Kundis, Cyril Brankyard, Martin Ringbauer, and Alessandro Fedrizzi. The title was Experimental Test of Local Observer Independence. The abstract stated the conclusion plainly. The violation implies that quantum theory should be interpreted in an observer-dependent way. Fedrizzi, the principal investigator, explained the result in interviews. The insight we gained is that quantum observers may indeed be entitled to their own facts. In an article for The Conversation, Fedrizzi and Proietti wrote that according to our best theory of the building blocks of nature itself, facts can actually be subjective. Let me be clear about what this does and does not mean. The experiment does not prove that your coffee table is subjective. It does not mean you can choose to believe the table is not there and it will stop being there. It does not support any variety of mystical thinking about consciousness creating reality. What the experiment shows is something more subtle and in some ways more disturbing. At the quantum level, measurement outcomes are not objective facts that all observers must agree upon. When one observer measures a system, the result is a fact for that observer. Another observer, describing the same situation from outside, may have a different fact. Both facts are correct. Neither observer is wrong. The laws of physics do not require that their facts agree. This is not a failure of knowledge. It is not that one observer knows the true fact and the other is simply mistaken. The experiment rules that out. Both observers are applying quantum mechanics correctly. Both are getting the results that quantum mechanics predicts. The results contradict each other because quantum mechanics does not provide a single objective reality for them to agree upon. You might object that photons are not real observers. That is a fair objection, and the authors anticipated it. But think carefully about what you are saying if you make that objection. You are saying that there is a category called real observers whose facts are objective, and another category called not real observers whose facts are subjective. You are drawing the Heisenberg cut, and you need to say where you are drawing it. Is a bacterium a real observer? Is a virus? Is a protein? Is a molecule? Where exactly does facthood become objective? What property does a system need to possess before its measurement results count as real facts about the world? If you say consciousness, you are back to Wigner's original proposal, and you inherit all its problems. How do you define consciousness? How do you measure it? How do you explain why consciousness has this magical power to make facts real? If you say complexity, you need to specify how much complexity. A photon in the Proietti experiment carries exactly 1 bit of information. A human brain carries roughly 2.5 petabytes of information, something like 2.5 million gigabytes. Is there some threshold between 1 bit and 2.5 petabytes where facts become objective? What is it? Why is it that number and not some other number? If you say nothing special is required, if you say facts are objective at all scales including photons, then you have to explain why the experiment violated the inequality. The math is clear. If observer-independent facts exist, the inequality is obeyed. The inequality was violated. The paper explicitly addressed this. One might further be tempted to deny our photonic memories the status of observer. This, however, would require a convincing revision of our minimal definition of what qualifies as an observer, which typically comes at the cost of introducing new physics. Nobody has produced that convincing revision. Nobody has introduced that new physics in a way that actually works. The challenge remains open. What the experiment establishes is a conditional. If you accept locality and freedom of choice, then you must reject observer-independent facts. You can escape the conclusion by rejecting one of the other assumptions instead, but each escape route has costs. Reject locality, and you allow instantaneous influences between distant events. Measurement choices made by Alice can instantaneously affect results obtained by Bob, even if Bob is across the galaxy. This is what Einstein called spooky action at a distance. It is permitted by quantum mechanics, but it seems to conflict with special relativity and with the entire causal structure of physics. Reject freedom of choice, and you accept superdeterminism. Every measurement choice you make was fixed at the Big Bang. The appearance of doing science is an illusion, because the experiments you run were predetermined to give the results they gave. You cannot test anything because you cannot make free choices about what to test. This interpretation is logically consistent, but it is scientifically nihilistic. It makes the entire enterprise of experimentation meaningless. Reject observer-independent facts and you accept that reality is perspectival. Different observers can have different facts about the same event. Measurement outcomes are real, but they are real for specific observers, not real in an absolute sense that all observers share. This is strange, but it may be the least strange of the options. Most physicists who work on foundations, when pressed, will admit that observer-independent facts is the assumption they would most readily sacrifice. Locality is precious because it underlies causality. Freedom of choice is precious because it underlies the ability to do science at all. Observer-independent facts feels essential until you realize that you have never actually proven it. You assumed it. Everyone assumed it. But assumptions can be wrong. There is an interpretation of quantum mechanics that has been waiting for this result. It was developed in 1996 by Carlo Rovelli, an Italian physicist known primarily for his work on loop quantum gravity. Rovelli called it relational quantum mechanics, and its central claim is that all physical properties are relational. They do not belong to systems in isolation. They are defined only relative to other systems. In relational quantum mechanics, there is no such thing as the state of the electron, full stop. There is only the state of the electron relative to this observer. A different observer may have a different state for the same electron. Neither state is wrong. Neither state is more real than the other. States are relationships, not properties. Rovelli explicitly compared this to special relativity. Before Einstein, physicists assumed that simultaneity was absolute. If two events are simultaneous for one observer, they are simultaneous for all observers. Einstein showed that this assumption is false. Simultaneity is relative to reference frames. Different observers, moving differently, will disagree about whether two distant events happened at the same time. Neither is wrong. Simultaneity is not an absolute property of events. It is a relationship between events and observers. Ravelli proposed that the same is true for quantum states. State is not an absolute property of a system. It is a relationship between the system and an observer. Different observers can have different states for the same system. Neither is wrong. State is not absolute. It is relational. When the Proietti experiment came out, relational quantum mechanics had a ready-made explanation. Of course, the inequality was violated. Of course, different observers have different facts. That is what the theory predicts. The friend has a definite fact relative to the friend. The Wigner has a different fact relative to the Wigner. Both facts are real in their respective relational contexts. There is no contradiction because there was never a requirement that all observers share the same facts. This is not solipsism. Ravelli is careful to emphasize this. Relational quantum mechanics does not say that reality is created by consciousness. It does not say that human minds are special. It says that facts are relative to physical interactions, not to mental states. A photon can be an observer. A rock can be an observer. Consciousness has nothing to do with it. What makes facts relative is not mind. It is interaction. When a system interacts with another system, properties become defined relative to that interaction. Before the interaction, the properties were not defined at all. After the interaction, they are defined relative to the interacting partner. A different interaction partner could define different properties. There is no God's eye view that sees all the properties as they really are. Another interpretation that handles the result comfortably is QBism, developed by Christopher Fuchs and collaborators. QBism treats quantum states as expressions of an agent's beliefs about future experiences. The wave function is not a description of reality. It is a description of what an agent expects to happen. Different agents can have different expectations. Different agents can have different quantum states. There is no conflict because there was never a claim that all agents share the same beliefs. In a 2020 paper titled Respecting One's Fellow, Fuchs and his collaborators analyzed Wigner's friend from the QBist perspective. They argued that no paradox arises because neither Wigner nor the friend claims to have objective access to the other's experience. The friend's measurement is a personal experience of the friend. Wigner's measurement is a personal experience of Wigner. Neither experience is privileged, neither is the real truth that the other's experience must conform to. QBism is more radical than relational quantum mechanics in some ways. It denies that quantum mechanics describes reality at all. Quantum mechanics describes expectations. What happens when those expectations are met or violated is outside the scope of the theory. But QBism shares with relational quantum mechanics the core response to Wigner's friend. There is no paradox because there is no requirement that different observers agree. Observer-independent facts was always an assumption, never a theorem. The assumption has been tested. The assumption fails. Many worlds offers a different escape. In many worlds, there is no collapse. When the friend measures the system, the universe splits. In one branch, the friend sees flash. In another branch, the friend sees no flash. Both branches are real. Both friends are real. There is no contradiction because the friends in different branches never meet. When Wigner opens the laboratory, he is also split. The Wigner who learns that the friend saw flash becomes correlated with the branch where the friend saw flash. The Wigner who learns no flash becomes correlated with the no flash branch. Every observer is having their experiences in the branch that is consistent with those experiences. The experiences never conflict because conflicting experiences happen in different branches. Many worlds preserves observer-independent facts in a sense. Within each branch, facts are objective. The friend in the Flash branch objectively saw Flash. This is a fact for everyone in that branch, but it is not a fact for observers in other branches. Facts are branch relative. The price of many worlds is the proliferation of branches. Every quantum event creates new branches. The universe is not one world, but an enormous and constantly splitting structure of parallel worlds. Most physicists find this ontologically extravagant. It seems to require far more reality than the phenomena demand. But many worlds has passionate defenders who argue that the extravagance is a feature, not a bug. The theory is simple. The wave function just evolves. No collapse, no measurement problem. The complexity is all in the interpretation of what exists. There are also objective collapse theories which take a completely different approach. These theories modify the equations of quantum mechanics, adding terms that cause superpositions to spontaneously collapse when they become too large or too complex. The most famous is the GRW theory, named after Garrardi, Rimini and Weber, who proposed it in 1986. In GRW, every particle has a small probability per unit time of undergoing a localization event. For a single particle, these events are so rare as to be undetectable. But when you have enough particles, like in a human brain, the cumulative effect of many localization events quickly collapses any superposition. Objective collapse theories would predict that the Bell-Wigner inequality is violated for photons, but not for human observers. The photons in Proietti's experiment are small enough that collapse does not occur. Human friends would be large enough that collapse has already happened before Wigner opens the laboratory. The friend would have a definite experience objectively, and Wigner's quantum description of the friend as being in superposition would simply be wrong. This is a testable prediction. If objective collapse theories are correct, then there should be a scale at which Wigner's friend experiments start obeying the inequality instead of violating it. Find that scale, and you have evidence for objective collapse. The current experiments do not probe this because photons are far below any proposed collapse threshold, but future experiments with larger quantum systems might. The difficulty is that objective collapse theories predict effects that have not been observed. The localization events should produce tiny amounts of heating. They should cause small deviations from standard quantum mechanics. So far, no such deviations have been found. The parameter space for objective collapse is getting squeezed from both directions. Experiments probing smaller systems that still show quantum behavior, and experiments looking for the signatures of collapse that do not find them. Finally, there is the option that almost no one takes, but that is logically available. You can reject freedom of choice, you can accept superdeterminism, you can say that everything was fixed from the beginning, that the experimenter's choices were determined by the prior state of the universe, that the correlations observed in the experiment were built into reality from the Big Bang. Superdeterminism makes the measurement problem go away, because there is no real measurement. There are no free choices. There are no genuinely open alternatives. The apparent randomness of quantum mechanics is not real randomness. It is determinism that we cannot predict because we do not have access to the relevant initial conditions. This view has some respectable defenders, including the Nobel laureate Gerard Hooft. But it has a devastating problem. If superdeterminism is true, then you cannot trust any experiment. The results of every experiment were predetermined. The conclusion you draw from the experiment was predetermined. The fact that you find the experiment convincing was predetermined. There is no way to use experimental evidence to support superdeterminism, because the entire concept of evidence presupposes that your evaluation of the evidence is not fixed in advance. Superdeterminism is unfalsifiable in the deepest sense. Not just that we happen not to know how to test it, but that testing itself becomes meaningless under the assumption. Most physicists regard this as a reason to reject superdeterminism, not as a reason to take it seriously. There is something worth noticing about all these escape routes. Each one saves objectivity in some domain by sacrificing it in another. Objective collapse theories preserve observer-independent facts, but make them scale-dependent. Many worlds preserves facts within branches, but multiplies the branches. Relational quantum mechanics and QBism preserve the reality of each observer's experience, but deny that those experiences need to cohere into a single story. Even superdeterminism, which preserves determinism, does so by eliminating the agent who could observe determinism at work. None of these moves restores the picture we started with. None of them gives us a single, observer-independent reality where facts are facts and truth is truth. That picture is gone. The experiments have taken it away. What we are choosing between now are different ways of living without it. The philosophical literature on these questions is vast and growing. Philosophers of physics have been working on the implications of Wigner's friend for decades, long before the experimental tests were developed. They have analyzed what it would mean for facts to be relative, what it would mean for observers to have different realities, what concepts of truth and knowledge would survive such a shift. The work is technical and careful. It does not support mystical conclusions or the abandonment of rationality. But it also does not provide easy answers. The philosophers do not agree among themselves about which interpretation is correct, or even about which questions are the right ones to ask. Philosophy does not have the experimental lever that physics has. Philosophy can clarify the options and analyze their consequences. It cannot tell us which option is true. What philosophy can tell us is that the options are genuinely different. Relational quantum mechanics is not the same as QBism, and neither is the same as many worlds. They disagree about whether reality is mind-dependent, about whether probabilities are subjective, about whether other branches exist. These are substantive disagreements with different implications for how we understand ourselves and our place in the universe. Relational quantum mechanics says that there is a physical world out there, independent of any mind, but that the facts about that world are relative to physical observers. The world is not constructed by consciousness, it is measured by physical interactions. A rock can be an observer, a photon can be an observer. The facts are relative to these physical interactions, not to experiences or beliefs. QBism says something different. QBism says that quantum states are not descriptions of the world. They are tools for an agent to organize their expectations about future experiences. The world is still there, according to QBism, but quantum mechanics does not describe it directly. Quantum mechanics describes the rational structure of beliefs. When I update my quantum state based on measurement, I am not discovering what the world is like. I am updating my expectations based on new experience. Many worlds says something different again. Many worlds says that the wave function is all there is. When you make a measurement, you do not collapse the wave function. You become entangled with the system, and both branches continue to exist. There are now two copies of you, one in each branch, each with their own experience. Neither copy is more real than the other. Both exist. These interpretations cannot all be correct. Relational quantum mechanics denies that there are multiple branches. QBism denies that quantum states describe external reality. Many worlds denies that collapse ever happens. At most, one of them can be true. Possibly none of them are true in their current form, and the correct picture will require ideas we have not yet developed. The experiment does not adjudicate between interpretations. What the experiment does is rule out a class of positions that all the interpretations are opposed to. The experiment rules out naive realism about facts. The experiment rules out the idea that measurements simply reveal pre-existing truths that all observers must agree on. The experiment forces everyone, regardless of their preferred interpretation, to accept that something has to change in how we think about the relationship between observers and facts. This is progress even if it is not resolution. Knowing what is wrong is valuable even when we do not yet know what is right. The history of science is full of cases where ruling out one option opened the door to discovering the correct option. Ruling out the luminiferous ether opened the door to special relativity. Ruling out classical mechanics at atomic scales opened the door to quantum mechanics. Ruling out observer-independent facts may open the door to something we cannot yet imagine. So where does this leave us? An experiment has been performed. The result is unambiguous. The laws of physics as we currently understand them do not require that different observers agree on the facts. Reality at the quantum level appears to be perspectival. This result was published in 2019. It should have changed the conversation about physics, about reality, about what it means for something to be true. It did not. Outside of specialist circles, almost no one knows about it. The headlines that appeared at the time, breathless articles about objective reality not existing, came and went like any other news cycle. They did not sink in. They did not change how people think. Part of this is the nature of the result. It is technical. It requires background knowledge to understand. The popular summaries inevitably distorted it, making it sound either more mystical or more trivial than it actually is. But part of it is something else. The result is uncomfortable. Not uncomfortable in the way that black holes are uncomfortable, vast and destructive and far away. Uncomfortable in a personal way. If observer-independent facts do not exist, then the assumption that underlies all of science, that experiments reveal objective truths about the world, is less stable than we thought. The community of scientists depends on shared facts. If facts are not shared, if your facts and my facts can legitimately differ, even when we measure the same system, then what is science even doing? The physicists who work on this know the implications. They do not talk about them loudly. The papers are careful and technical. The conclusions are hedged with caveats about interpretation and experimental limitations. Nobody wants to be the person who declares that objective reality is dead. That is not how science works. You publish your result, you explain what it means, you let the community evaluate it. But the community has not really evaluated it. The community has mostly ignored it. Foundations of physics is a small subfield, often regarded as vaguely disreputable by physicists who do real work on particle physics or condensed matter or cosmology. The big questions about measurement and reality are treated as philosophical, which in physics is often a polite way of saying not worth spending time on. The 2022 Nobel Prize went to Alain Aspect, John Clauser, and Anton Zeilinger for their Bell test experiments. This was recognition that testing the foundations of quantum mechanics is Nobel-worthy work. But the prize was for experiments done decades ago. The newer results, the Wigners friend experiments, the violations of Bell-Wigner inequalities, these have not penetrated the public consciousness, or even the consciousness of most physicists. Meanwhile, the research program continues. In 2020, a team led by Howard Wiseman at Griffith University in Australia published a paper in Nature Physics called A Strong No-Go Theorem on the Wigners Friend Paradox. They derived new inequalities, called local friendliness inequalities, that are even stronger than the Bell-Wigner inequality. Local friendliness inequalities can be violated by quantum mechanics, even in scenarios where Bell inequalities are not violated. This establishes a new hierarchy of non-classical correlations. The quantum world is even stranger than Bell tests alone revealed. In 2023, the Paul Ehrenfest Best Paper Award for Quantum Foundations was given jointly to 3 papers. Bruckner's 2018 paper on Bell-Wigner inequalities, Frauchiger and Renner's paper on quantum theory not consistently describing itself, and the Bong et al. Paper on local friendliness. The award committee stated that these theorems provide new challenges for the interpretation of quantum theory, forcing us to make some hard choices in our conception of quantum reality. Forcing us to make some hard choices. That is a polite way of saying that something has to give. We cannot keep all our intuitions about reality. The experiments are telling us that at least one of our deep assumptions is wrong. The choice of which assumption to abandon is ours, but we cannot refuse to choose. The data does not allow it. And yet most of the world does not know this choice is being forced. Most of the world does not know that experiments have been performed. Most of the world assumes that reality is one thing that we all share, that facts are facts, that if you and I measure the same system, we will get the same answer. The assumption is false, or at least the assumption is in tension with our best theory of physics. And when the theory was tested, the theory won. You can reject the theory if you want, but then you need a better theory, and nobody has one. What you cannot do is pretend the experiments did not happen. The experiments happened. The data exists, and every escape route from what the data implies requires you to give up something you probably thought was not negotiable. Think carefully about what each option costs. Think about what it would mean to accept each alternative. Think about how your picture of reality would have to change depending on which assumption you abandon. If you give up locality, you live in a universe where what happens here can instantaneously depend on what happens there, no matter how far away there is. Your measurement choice in Edinburgh can affect outcomes in Tokyo with no delay whatsoever. This is not just strange. It makes the entire framework of causal reasoning suspect. If effects can depend on arbitrarily distant causes with no time delay, how do you ever isolate a system well enough to study it? How do you know that your experiment results are not being influenced by something happening on the other side of the galaxy right now? If you give up freedom of choice, you live in a universe where your decisions are illusions. You think you chose to read this far into this explanation. You think you could have stopped at any point. You think you are evaluating the arguments and deciding whether to accept them. But if freedom of choice is false, then you had no choice. Your apparent decision was fixed by the initial conditions of the universe set in motion billions of years before you were born. The correlation between your choices and the experimental outcomes was not a result of the experiment. It was built into the fabric of reality from the beginning. If you give up observer-independent facts, you live in a universe where reality is perspectival. What happened depends on who you ask. Different observers can have different answers, and both answers can be correct. There is no view from nowhere, no God's eye perspective that sees what really happened. There are just views from somewhere, and the views do not need to agree. Each of these alternatives is disturbing in its own way. Each requires abandoning something that seemed obvious, something that seemed necessary for making sense of the world. The experiment has cornered us. We must choose. But there is no choice that leaves our worldview intact. Think carefully about what each option costs. If you want to keep observer-independent facts, you have to give up either locality or freedom of choice. Giving up locality means accepting that your measurement choices here can instantaneously influence outcomes there, even if there is on the other side of the universe. This is not just faster than light signaling, it is instantaneous causation across arbitrary distances. The entire structure of physics, the idea that causes precede effects, that influences propagate through space, would need to be rebuilt. Special relativity does not prohibit correlations between distant events, which is why standard Bell test violations are consistent with relativity. But the correlations required to maintain observer-independent facts in a Wigner's friend scenario go further. They require genuine action at a distance. The physics community has not found a way to make this work. Giving up freedom of choice means accepting superdeterminism, that your choice of what experiment to run was fixed at the Big Bang, that the correlation between your choices and the experimental outcomes was built into the initial conditions of the universe. This preserves observer-independent facts by denying that you ever had a choice in the first place. The appearance of experimentation is an illusion. You were always going to run that experiment, get that result, draw that conclusion. There is no way to test this hypothesis because testing requires making choices, and the hypothesis says choices are not real. Superdeterminism is consistent with all data because it is consistent with all possible data. It explains everything by explaining nothing. Most physicists, when forced to choose, will sacrifice observer-independent facts. Locality is too precious. It underlies causality, the arrow of time, the entire framework that lets us do physics. Freedom of choice is too precious. It underlies the scientific method itself, the ability to design experiments and learn from their results. Observer-independent facts feels essential until you realize it was always an assumption. We believed it because it seemed obvious. But obvious beliefs have been wrong before. The Earth seems obviously stationary. The Sun seems obviously to revolve around us. Simultaneous events seem obviously simultaneous for everyone. Each of these obvious beliefs turned out to be false. The Earth moves, the Sun is stationary relative to us. Simultaneity depends on your reference frame. Science progresses by abandoning obvious beliefs when evidence contradicts them. Observer-independent facts is the next obvious belief on the chopping block. Two observers measuring the same system will get the same result. Facts are facts regardless of who establishes them. Reality is one thing that we all share. These statements feel like they must be true. The experimental evidence says otherwise. But here is what the experiment does not show. It does not show that reality is an illusion. It does not show that you can believe whatever you want and make it true. It does not show that consciousness creates reality or that mystical thinking has been vindicated by physics. The experiment shows that reality may be observer-relative without being observer-created. The facts that you establish are real facts. They are just your facts. Another observer may have different facts. Those facts are also real. The difference is not a matter of belief or interpretation, or perspective in the casual sense. The difference is a feature of the physics. The laws do not require agreement. This is the misconception that trips people up. They hear observer-dependent and think subjective. They think the experiment proves that reality is whatever you want it to be. That is not what the experiment shows. The experiment shows that the concept of a single objective reality, one set of facts that all observers share, is not built into the laws of physics. It was an assumption. The assumption fails at the quantum level. Your coffee table is still there. You cannot wish it away. The reason is that you and the coffee table have already interacted. You have already established facts about each other through countless physical interactions. Those facts are stable because decoherence has made them robust against interference from other branches or perspectives. The quantum weirdness is real, but it is hidden beneath layers of thermodynamic irreversibility. By the time anything reaches the scale of tables and chairs and human beings, the observer dependence has been washed out by the sheer number of interactions. But washed out is not the same as eliminated. The observer dependence is still there. Underneath. It is the foundation on which the apparently objective world is built, and the foundation, as the experiment shows, does not support the weight we thought it could carry. There is a question that I have been avoiding, and I need to address it directly. If facts are observer-relative, what does that mean for you? Not for photons in a laboratory, not for thought experiments involving sealed rooms and quantum coins. For you, reading this, living your life, interacting with other people who you assume are experiencing the same reality you are. The honest answer is that nobody knows. The experiment was performed with photons. Photons are quantum systems that can be isolated and manipulated with extraordinary precision. Human beings are not. Human beings are warm, wet, noisy systems, embedded in an environment that is constantly interacting with them. The decoherence time for a human brain is so short that it might as well be zero. Any quantum superposition involving your neurons collapses effectively instantly. So in one sense, the experiment has no implications for your daily life. You will never be in a quantum superposition. You will never experience the kind of ambiguity that the friend photon experiences. Your facts will always feel definite to you because they are definite relative to you. But in another sense, the experiment has profound implications. It tells you something about the deep structure of reality. It tells you that the definiteness you experience is not a feature of the universe itself. It is a feature of your relationship with the universe. Another observer, sufficiently isolated from you, could have a different relationship, different facts, both real. The many worlds interpretation handles this by saying that you are constantly branching. Every quantum event in your brain creates new copies of you in new branches. The you reading this sentence is one of countless copies, each having slightly different experiences, each equally real. The copies never meet because the branches do not interfere, but they are all there, all experiencing their own versions of reality. Relational quantum mechanics handles it differently. There are no copies, there is just you with your facts. Another observer has their facts. The facts do not need to agree because there is no absolute standard for them to agree with. Agreement happens when observers interact and share information. When you tell someone what you experienced and they tell you what they experienced, you are establishing shared facts through communication. But those shared facts are still relative to the community of observers who have communicated. An observer outside that community might have different facts. QBism is more radical still. The facts are your experiences. Full stop quantum mechanics does not describe an external world. It describes your expectations about your future experiences. When those expectations are confirmed or violated, that is what measurement is. There is no reality behind the experiences. There are just experiences. Each of these interpretations is consistent with the experimental data. Each requires giving up something that feels essential. Many worlds asks you to accept an infinite proliferation of equally real copies of yourself. Relational quantum mechanics asks you to accept that there is no view from nowhere, no God's eye perspective on what really happened. QBism asks you to accept that physics describes beliefs rather than reality. The choice is yours. The experiment does not tell you which interpretation is correct. It tells you that observer-independent facts must be abandoned if you want to keep locality and freedom of choice. How you abandon observer-independent facts, which framework you use, that remains open. What is not open is pretending the problem does not exist. What is not open is continuing to assume that reality is one thing we all share, that facts are objective, that measurement reveals pre-existing truths about the world. That assumption has been tested. It failed. The question nobody seems willing to ask in public is what this means for science itself. Science is built on the idea that experiments reveal objective truths. You do an experiment, you get a result. The result is true for everyone. Other scientists can replicate your experiment and get the same result. That is what makes science science. It is not just opinion. It is not just one person's perspective. It is objective knowledge about the world. But if observer-independent facts do not exist, what does replication even mean? If your facts can differ from my facts and both be correct, then what does it mean to say that I replicated your experiment? We might both be right while disagreeing about what happened. The standard response is that this problem only arises at the quantum level. For macroscopic experiments, The ones that science actually cares about, decoherence ensures that all observers agree. The observer dependence is washed out before it can matter. Science proceeds as usual. This response is probably correct. But it is worth noticing that it is a contingent response, not a principled one. It says that observer dependence does not matter in practice, not that observer dependence does not exist. The foundations are still cracked. We have just built high enough above the cracks that the building still stands. For now, the other question nobody wants to ask is whether the observer dependence might extend further than we think. The experiments so far have used photons. The decoherence time for photons in these experiments is long enough to observe quantum effects. What about larger systems? What about systems that are quantum but more complex than photons? In 2019, the same year as the Proietti experiment, a team in Vienna demonstrated quantum interference with molecules of over 800 atoms. These molecules are large enough to see under an electron microscope. They are not macroscopic in the everyday sense, but they are far larger than photons. If you could perform a Wigner's friend experiment with molecules instead of photons, would the inequality still be violated? Nobody has done this experiment yet. The technical challenges are immense. Molecules decohere faster than photons. The interference effects are harder to observe. The 6-photon coincidence rate that made the Proietti experiment so painstaking would be nothing compared to the difficulties of working with entangled molecules. But there is no theoretical reason why the inequality would be obeyed for molecules and violated for photons. Quantum mechanics does not distinguish between them. The Bruckner framework applies to any quantum system. If observer-independent facts fail for photons, they should fail for molecules too. And if they fail for molecules, they should fail for anything that can be placed in a quantum superposition. The question is where quantum superposition stops. Is there a scale at which superposition becomes impossible? Objective collapse theories say yes. At some point, around the scale of viruses or small dust grains, spontaneous collapse kicks in, and superposition is destroyed. But objective collapse theories are increasingly constrained by experiments that show quantum effects at larger and larger scales. The collapse threshold, if it exists, keeps receding. If the collapse threshold does not exist, if quantum mechanics is universal, then observer dependence is universal too. The only reason you do not notice it is decoherence. Decoherence hides the observer dependence. It does not eliminate it. This is the implication that keeps physicists up at night. Not that photons have observer relative facts. Photons are weird. We have known that for a century. What keeps them up is the suspicion that the observer relativity goes all the way up, that the apparently objective world of tables and chairs and other people is built on a foundation of observer relative facts, that the agreement we experience is not a feature of reality, but a consequence of communication, of shared history, of interacting systems establishing correlations through physical contact. If relational quantum mechanics is right, then you and the person you are talking to do not inhabit the same reality. You inhabit compatible realities. Your facts and their facts are correlated because you have interacted. The correlation is strong enough that you can communicate, strong enough that you feel like you are sharing the same world. But the sharing is an achievement, not a given. It is built through interaction, not assumed from the start. And if you encountered an observer sufficiently isolated from you, an observer whose history had not correlated with yours, their facts might differ from yours in ways that could never be reconciled. Not because one of you is wrong, because facts are relative, and relative facts can diverge. There is something else that needs to be said about the cost of abandoning observer-independent facts. It is not just an abstract philosophical price. It reaches into how you understand your relationships, how you understand the very act of knowing anything at all. Consider memory. You remember things that happened to you. Those memories feel like records of objective events. You were there. You saw what happened. The memory is stored in your neurons, a physical trace of a physical event. When you recall the memory, you are retrieving information about reality. But if facts are observer relative, then what you are remembering is not an objective event. You are remembering your fact, your event, your reality. Another person who was present might remember something different, not because one of you is misremembering, because you experienced different facts. Your memories are both accurate records of different realities. This sounds like it should lead to chaos. If everyone has different facts, how can we have courts of law, historical records, science itself? The answer is that decoherence and interaction create effective objectivity at macroscopic scales. By the time events are large enough and complex enough to involve human observers, the quantum relativity has been washed out. The facts you remember and the facts others remember are correlated by the physical processes that created those memories. The correlation is strong enough that disagreements are usually about interpretation, not about what happened. But the correlation is not perfect, and the correlation is a physical achievement, not a logical necessity. The universe does not guarantee that your memories match other people's memories. It only guarantees that your memories are consistent with your interactions. Since your interactions overlap with other people's interactions, your memories tend to agree. But tending is not the same as must. Consider the implications for personal identity. You think of yourself as a continuous being, a single person who persists through time. Your sense of identity is based on memory, on the feeling that the person who woke up this morning is the same person who went to sleep last night. But if facts are observer relative, then the you of yesterday and the you of today are not straightforwardly the same observer. The facts established yesterday were established by yesterday's you. Today's you has access to those facts only through memory, only through the physical traces left by yesterday's interactions. In a sense, you are constantly inheriting your own history. The you of this moment is correlated with the you of previous moments by the physical continuity of your brain and body. But the correlation is what gives you access to your past, not identity in some deeper metaphysical sense. You are a chain of observer moments, each one passing facts to the next through physical processes. This might sound like Buddhist philosophy or like certain theories in analytic philosophy of mind. It is both of those things, and neither. It is both because these ideas have been explored before in different contexts. It is neither because the experimental result grounds the speculation in physics. This is not just one possible way of thinking about identity. It is a consequence of taking quantum mechanics seriously, of accepting what the experiments show about the observer relativity of facts. The implications for knowledge are equally destabilizing. Knowledge is traditionally defined as justified true belief. You know something if you believe it, if your belief is justified by evidence, and if it is true. But if truth is observer relative, what does it mean for a belief to be true? The natural answer is that truth is relative to the observer. A belief is true for you if it matches your facts. It might not be true for someone else if their facts differ. This is not the same as relativism in the popular sense, the idea that everyone is entitled to their own truth and nobody can say who is right. The facts are not arbitrary, they are established by physical interactions. You cannot choose your facts, you can only discover them through measurement. But the facts you discover are yours. They are real, they are not negotiable, and they might not be the same as the facts discovered by another observer. In the quantum regime, this is experimentally verified. In the classical regime, decoherence makes the differences negligible. But negligible is not zero. The philosophy of science will eventually have to grapple with this. The current philosophy of science assumes that scientific knowledge is objective, that well-conducted experiments reveal truths that all observers must accept. This assumption is operational in the sense that it works well enough for practical purposes, but it is not foundational. The foundations do not support objective truth. They support observer relative truth that happens to be correlated across observers sufficiently that we can do science. This is a weaker foundation than we thought we had. It might be strong enough. It might be that the correlation is so robust that the difference between objective truth and correlated relative truth is never practically relevant. But it is a different foundation. And understanding the difference matters for understanding what science is and what it can tell us. Enough philosophy, let me return to the history, to the story of how this result came to be ignored. This brings me to the silence. In 2019, when the Proietti experiment was published, there was a flurry of media coverage. MIT Technology Review ran a headline declaring that a quantum experiment suggests there is no such thing as objective reality. The article went viral. Science journalists picked up the story. For a few weeks, it seemed like the foundations of physics might actually enter public consciousness. Then the news cycle moved on. The story faded. Other things happened. The implications of the experiment never sank in. You might think this is normal. Scientific results take time to percolate. The public cannot be expected to absorb every breakthrough immediately. Give it a few years and the significance will become apparent. It has been more than 6 years. The significance has not become apparent. Outside of a small community of specialists, almost nobody knows about the experiment. Almost nobody knows that observer-independent facts have been experimentally challenged. Almost nobody knows that the assumption underlying all of science, the assumption that experiments reveal objective truths, is now questionable. This is not an accident. This is a choice. The physics community knows about these results. The papers have been published in top journals. They have been cited hundreds of times. The theoretical frameworks have been developed and refined. The experiments have been replicated and extended. The 2023 Ehrenfest Award recognized the foundational importance of this work. The community knows. Not publicly, not to general audiences. The popular physics books that come out every year, the ones about black holes and the Big Bang and quantum computing, they do not mention Wigner's friend experiments. The physics documentaries on streaming platforms do not cover them. The science journalists who write about the wonders of quantum mechanics do not explain what observer-dependent facts would mean for everything else. There are reasons for this silence, and the reasons are understandable. The result is technical. It is easy to misunderstand. The headlines that did appear in 2019 were often misleading, making it sound like reality is an illusion, or that consciousness creates the universe. Physicists do not want to feed mystical misinterpretations. They do not want to give ammunition to cranks. There is also the professional incentive structure. Foundations of physics is not where careers are made. The big grants go to particle physics, to cosmology, to quantum computing. A young physicist who spends too much time on interpretational questions risks being seen as not serious. The implicit message from the establishment is that these questions are interesting but not important. You can think about them as a hobby, but do not let them distract you from real work. And there is the discomfort. The result implies that something is wrong with how we think about reality. Scientists do not like admitting that something is wrong with how they think about reality. The entire enterprise of science depends on objective facts being real. If objective facts are not real, what is science even doing? It is easier to not think about it, to focus on the calculations, to shut up and calculate. But the silence has a cost. The cost is that the public does not know. The cost is that people go on assuming that science reveals objective truths, that facts are facts, that reality is one thing we all share. They assume this because physicists let them assume it. Physicists know better, but physicists do not say so. I am not accusing anyone of conspiracy. There is no meeting where senior physicists decide to suppress the implications of Wigner's friend experiments. There is just a collective shrug, a sense that this is not the kind of thing you talk about in public, a preference for letting sleeping dogs lie. But the dogs are not sleeping. The research program is active. New papers appear every month. The local friendliness inequalities from 2020 were just the beginning. In 2021, Guerin, Baumann, Del Santo, and Bruckner proved that a friend's perceived outcomes at different times cannot share the same reality under standard quantum assumptions. In 2022, Bruckner published a perspective in Nature Reviews Physics on relational objectivity. In 2023, Wiseman, Cavalcanti, and Riefel designed a refined local friendliness experiment suitable for implementation on a quantum computer. In 2024, Baumann and Bruckner showed that if a friend were somehow aware of changes to their own memory, it would violate the no-signaling principle, which would be even stranger than observer-dependent facts. The field is advancing, the questions are getting sharper, the implications are getting harder to avoid. Sooner or later, the silence will break. The 2022 Nobel Prize in Physics went to Alain Aspect, John Clauser, and Anton Zeilinger. The citation was for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. This was recognition, finally, that testing the foundations of quantum mechanics is not just philosophy, it is Nobel-worthy physics. But notice what the prize was for: Bell inequalities. Work from the 1970s and 80s, the Wigners friend experiments, the ones that go further, the ones that challenge observer-independent facts, those were not mentioned. The Nobel Committee recognized the importance of Bell tests, while staying silent on the experiments that extend Bell tests into even more uncomfortable territory. I do not know if this was deliberate. The Nobel Committee does not explain its reasoning. But the pattern is clear. The physics establishment is willing to acknowledge that local realism is dead. It is not yet willing to acknowledge that observer-independent facts might be next. Consider the contrast. When the Bell test loopholes were finally closed in 2015, it was front-page news. Experiments had definitively ruled out local hidden variables. The correlations predicted by quantum mechanics were real and could not be explained by any theory in which particles have predetermined properties independent of measurement. This was presented as a triumph, a final vindication of quantum weirdness. But the Wigner's friend experiments rule out something arguably more fundamental. Not hidden variables, which were always a technical assumption that most physicists did not believe in anyway. Observer-independent facts. The assumption that when you measure something and get a result, that result is objectively true. The assumption that underlies not just quantum mechanics, but all of empirical science. Where are the headlines? Where are the documentaries? Where is the Nobel Prize? The silence is the scandal. Not because there is a cover-up, because there is no cover-up. The information is public. The papers are available to anyone. The silence is just inertia, just embarrassment, just a preference for not dealing with uncomfortable implications. And the result is that you did not know. Until now, if you are like most people, you had no idea that this experiment had been performed. You had no idea that the objectivity of facts is experimentally questionable. Think about what that means. Think about all the conversations you have had about science, about reality, about what we know and how we know it. Think about all the debates about truth and facts and evidence. None of those conversations included the information that observer-independent facts have been experimentally challenged. None of them mentioned that physics has produced data suggesting that facts are relative to observers. This is not obscure trivia. This is not a minor technical result buried in a specialized journal. This is a 5 sigma experimental violation of an inequality that tests whether objective reality exists. If any other experimental result with implications this profound had achieved 5 sigma, it would be headline news. It would be in textbooks. It would be part of the common understanding of educated people. Instead, it is almost unknown. The few headlines that appeared in 2019 were quickly forgotten. The result did not change how anyone outside of specialist circles thinks about reality. The assumption that facts are objective persists unexamined in nearly everyone's worldview. Part of the reason is that the result is hard to explain. It requires understanding quantum entanglement, Bell inequalities, the measurement problem. These are not concepts that most people have encountered. The journalists who covered the story in 2019 struggled to convey what the experiment actually showed. Many of the headlines were misleading. "Objective reality does not exist," proclaimed MIT Technology Review. But that is not quite right. The experiment does not show that objective reality does not exist. It shows that observer-independent facts do not hold at the quantum level. The distinction matters, but it is subtle enough that popular accounts consistently get it wrong. Another part of the reason is that physicists themselves are uncomfortable with the result. The foundations of physics community takes it seriously. They publish papers, hold conferences, refine the theoretical frameworks. But most physicists are not in the foundations community. Most physicists work on applications, on quantum computing, on condensed matter, on particle physics. They use quantum mechanics without worrying about what it means. The measurement problem is something they learned about in graduate school and then forgot. It is not relevant to their daily work. When physicists are asked about interpretations of quantum mechanics, many of them roll their eyes. This is considered a soft topic, not real physics. The famous physicist David Neumann coined the phrase, "shut up and calculate," to describe the attitude. Do the math, get the predictions, check against experiment. Do not worry about what it all means. Meaning is for philosophers. This attitude has been dominant for decades. It was arguably appropriate when the questions were purely interpretational, when no experiment could distinguish between Copenhagen and many worlds. And pilot wave theory, if the choice of interpretation makes no empirical difference, you can reasonably argue that it is not a scientific question. But the Wigners' friend experiments change that. The choice of interpretation now has empirical teeth. If you believe in observer-independent facts, you must accept either non-locality or superdeterminism, and both of those have potential empirical signatures. If you believe facts are observer-relative, you must explain where the objectivity we observe in daily life comes from. And that explanation involves decoherence, which is a physical process that can be studied experimentally. The interpretational questions are becoming empirical questions. The shut up and calculate attitude is becoming obsolete. But old attitudes die hard, and the physics community has not yet fully absorbed the implications of what the experiments show. There is also a sociological factor. Physicists who work on foundations are often viewed with suspicion by their colleagues. Foundations research has historically attracted cranks and mystics who see quantum mechanics as validation for their beliefs. Serious physicists who work on foundations have to constantly distinguish themselves from the cranks. They have to prove that their work is rigorous, mathematical, testable. This creates a defensive posture. Foundations physicists are reluctant to make strong public claims because they know how easily those claims can be misinterpreted or co-opted by people with questionable agendas. The result is a community that speaks quietly among itself but does not project its findings into the broader culture. The papers are published in technical journals read by specialists. The conferences are attended by a small group of researchers who already know each other. The insights are shared within the community, but not beyond it. This is not conspiracy. It is the sociology of a small academic field operating under hostile conditions. The hostility comes from mainstream physics, which sees foundations as not real work, and from the public, which is prone to misunderstanding quantum mechanics as validation for mysticism. Caught between these pressures, foundations physicists have retreated into their community and stopped trying to explain their results to outsiders. The cost is that outsiders do not know. The cost is that you did not know. The cost is that the most profound experimental results in physics are effectively invisible to the educated public. I am trying to change that. I am telling you what the experiments show as clearly and accurately as I can. I am not a physicist. I am a communicator, translating technical results into language that non-specialists can understand. The translation inevitably loses precision. The full story is in the papers, which are publicly available for anyone who wants to read them. But the gist, the core finding, the thing you need to know is this: observer-independent facts at the quantum level do not hold. The experiments have spoken. The assumption is falsified. The man who started all this died in 1995. Eugene Wigner never saw his thought experiment turned into a real experiment. He never saw the Bell-Wigner inequality violated by 5 standard deviations. He never had to confront the possibility that his question about his friend had an answer, and that the answer was that observer-independent facts do not exist. Would he have been satisfied? Probably not. Wigner spent his last decades convinced that quantum mechanics itself needed revision. He did not believe that any existing interpretation adequately resolved the measurement problem. He would likely have looked at the 2019 result and said, yes, this confirms what I suspected, but it does not tell us how to fix it. And he would have been right. The experiment tells us what fails. It does not tell us what succeeds. It eliminates observer-independent facts as a viable assumption. It does not hand us a replacement. The interpretations that remain, relational quantum mechanics, QBism, many worlds, these are not solutions. They are frameworks for thinking about a problem that has no solution yet. The irony of Wigner's career is that he kept being right for the wrong reasons. In 1961, he proposed that consciousness collapses the wave function. He was wrong about consciousness, but right that there was a problem with how quantum mechanics handles observers. In the 1980s, he abandoned consciousness, but insisted that quantum mechanics needed revision. He was wrong about needing new equations, but right that our interpretation needed fundamental change. He kept circling the truth without quite landing on it. The Hungarian genius who sat 1 year ahead of von Neumann, who helped design the plutonium reactors that ended World War II, who won the Nobel Prize for discovering symmetry principles in nuclear physics, that man could not solve the problem of his friend. The thought experiment he proposed in a collection of partly baked ideas outlived him. It became more important after his death than it was during his lifetime. And the answer it eventually received was stranger than anything he imagined. Consider the trajectory: a speculative essay in 1961, decades of debate among philosophers and physicists, a theoretical breakthrough in 2018, showing how to turn the speculation into a test, an experimental result in 2019, showing that the test was violated, a continuing research program pushing the results further, closing loopholes, exploring implications. The arc from thought to experiment to confirmed result took nearly 60 years. Wigner saw only the first 40 of those years. He died before the story was finished. His friend Massimiliano Proietti, the PhD student who ran the decisive experiment, had not been born when Wigner proposed his thought experiment. The generations do not overlap. The old physicist poses a question, dies, and decades later a young physicist answers it. This is how science works. The timescales exceed individual lifetimes. The questions outlast the people who ask them. But there is something poignant about Wigner's absence from the conclusion. He asked whether his friend could have a fact about a quantum system, while he himself had a different fact. He asked whether observer-independent facts are real. He spent decades thinking about this question, wrote about it, changed his mind about what the answer might be. Then he died, and then the experiment was done, and then the answer came, no. Observer-independent facts, at least at the quantum level, are not real. The friend has their fact. Wigner has his. Neither is wrong. Neither is more real than the other. If Wigner were alive to hear this, what would he say? I imagine something characteristically understated. Something like, I suspected as much, but I could never quite believe it, and I still do not know what to do with it. Neither do we, but there is something valuable in knowing what fails. Science often progresses by ruling things out. You cannot always discover the right answer directly. Sometimes you have to eliminate the wrong answers one by one until the right answer is the only one left standing. Observer-independent facts was a wrong answer, or at least, it was a wrong assumption. For centuries, we assumed that the facts revealed by measurement were objective features of the world, independent of who measured them. The assumption seemed so obvious that nobody thought to question it. The assumption is now questionable. What replaces it is still unclear. Relational facts. Maybe. Facts that are real but relative to observers. Facts that do not need to agree because there is no absolute standard for agreement. Facts that are established through interaction and can vary between observers who have not interacted. This is not a comfortable picture. Humans want objective truth. We want a reality that is one thing, shared by everyone, the same for all observers. We want our facts to be the facts, not just our facts. The experiment suggests that this want cannot be satisfied at the quantum level, and maybe not at any level. But discomfort is not an argument. The universe does not care what we want. The universe is what the experiments say it is. And the experiments say that observer-independent facts, at least for photons, at least in the carefully controlled conditions of the Edinburgh laboratory, do not hold. There is one more thing to consider. The implications extend beyond physics into how we think about disagreement, about truth, about the possibility of shared understanding. We live in an era when people talk about living in different realities. Political polarization has created communities that seem to inhabit different worlds with different facts, different truths, different versions of what has happened and what it means. This is usually discussed as a failure, a breakdown of the shared epistemic commons that democracy requires. The quantum experiments do not validate this social phenomenon. They do not prove that political tribalism is somehow natural or inevitable. The observer relativity of facts at the quantum level is a precise physical phenomenon with specific conditions and constraints. It is not a metaphor for people believing whatever they want, but there is a connection, not causal but conceptual. The experiments reveal that unity of facts is not guaranteed by the structure of reality. Unity of facts at the quantum level must be achieved through interaction. It is not given for free. It is built by the physical processes that correlate observers with each other and with the systems they measure. Perhaps something similar is true at the social level. Perhaps unity of facts among humans is not guaranteed either. Perhaps it must be built through communication, through shared experience, through the hard work of establishing common ground. Perhaps the assumption that we automatically share a common reality was always too optimistic, and the social fragmentation we observe is what happens when the assumption is no longer maintained. This is speculation. The quantum experiments do not prove anything about social epistemology, but they shift the default assumption. They suggest that shared reality is an achievement rather than a given. They suggest that disagreement might be more fundamental than we thought, and agreement more remarkable. If observer-independent facts do not exist at the quantum level, and the quantum level underlies everything, then perhaps the objective world we seem to inhabit is more fragile than it appears. Perhaps it is held together by the constant interactions that correlate our experiences, by the decoherence that washes out the quantum relativity, by the communication that synchronizes our descriptions. Perhaps if those interactions stopped, if the correlations were disrupted, the unity of reality would dissolve. This is probably not something to worry about in practice. The interactions are robust. The correlations are established by physics, not by human effort. You do not have to work to stay in the same reality as the person next to you. The universe handles that automatically. But it is something to think about. The unity we experience is not metaphysically necessary. It is physically contingent. It depends on how quantum mechanics works, on how decoherence operates, on how observers are embedded in their environments. A universe with different physics, or even this universe under different conditions, might not have shared reality at all. We are lucky, in a sense, lucky that the quantum relativity is hidden beneath layers of interaction, lucky that we live in a regime where facts seem objective, where reality seems shared, where disagreement can at least in principle be resolved by checking the evidence. That regime is not the only possible regime. It is a feature of our location in parameter space, not a necessary truth about all possible worlds. In 2019, Massimiliano Proietti and his collaborators at Heriot-Watt University ran an extended Wigners friend experiment. They used 6 photons, 3 entangled pairs, a precisely tuned laser, and weeks of painstaking data collection. They measured correlations between the choices of 2 external observers and the results recorded by 2 internal observers, where the internal observers were photons whose polarization states served as measurement records. They computed the Bell-Wigner parameter S, which must be less than or equal to 2 if locality, freedom of choice, and observer-independent facts are all true. The value they found was greater than 2 by 5 standard deviations. The inequality was violated. At least one of the 3 assumptions must be false. If you accept locality, and you should, because locality is what makes causality work, if you accept freedom of choice, and you should, because freedom of choice is what makes experimentation possible, then you must reject observer-independent facts. 2 observers can measure the same quantum system and get results that are individually correct but mutually contradictory. Not because of error, not because of different perspectives on the same underlying truth, because both results are real. Both realities are real. The experiment does not prove that one observer is wrong. It proves that the concept of one observer being wrong presupposes an objective reality that they could be wrong about. If there is no objective reality, if facts are relative to observers, then both observers are right. Their facts differ because facts are allowed to differ. But the part nobody can explain is what replaces objective reality. If there is no shared reality, then there is no fact of the matter about anything until a specific observer interacts with it. Before interaction, there are only potentialities, not actualities. After interaction, there are actualities, but they are relative actualities. Actualities for this observer, not actualities, period. Your reality is yours. It is not wrong. It is not incomplete. It is not a distortion of some deeper objective reality that you fail to perceive. It is just yours. Another observer has their reality. It is also not wrong. The 2 realities do not need to agree because there is nothing for them to agree about. There is no meta-reality that serves as the standard. There are just realities, plural, observer-relative, potentially different. And the laws of physics do not require that they ever converge. Convergence happens when observers interact and share information. But convergence is a physical process, something that occurs through actual physical interaction. It is not guaranteed by the structure of reality. It is achieved by the dynamics of specific systems in specific situations. You and every person you have ever spoken to may have been living in compatible but fundamentally different realities for your entire lives. Compatible because you have interacted, because decoherence has correlated your facts, because communication has synchronized your descriptions of what happened. But fundamentally different because facts are relative, and relative facts established by different observers need not be the same. The word may, in that sentence, is generous. The experiment suggests not that this might be the case, but that it is the case. The experiment does not directly probe human observers, but it probes quantum observers, and there is no principled reason why human observers should be exempt from the same physics that governs photons. We are made of quantum systems. We interact with quantum systems. If quantum systems have observer-relative facts, we do too. The difference is scale. The difference is complexity. The difference is decoherence. At the scale of photons, observer relativity is manifest. At the scale of humans, observer relativity is hidden. But hidden is not absent. The relativity is still there, underneath, at the foundations of everything. What does it mean to share an experience with someone if you are not sharing a reality? What does it mean to remember something together if your memories are of different facts? What does it mean to love someone if the person you love inhabits a different reality than you do, one that merely overlaps with yours sufficiently for communication to proceed? These questions do not have answers yet. The physics is too new. The philosophy has not caught up. We're in the early stages of a conceptual revolution that may take decades to complete. The experiment that started it was performed only 6 years ago. The theoretical frameworks that make sense of it are still being developed. But the direction is clear. Objective reality, the old assumption, the comfortable assumption, the assumption that let us believe we all share the same world, that assumption is dying. Something will replace it. We do not yet know what. But we know what it will not be. It will not be observer-independent facts. It will not be observer-independent facts. It will not be the world as we used to think it was. The Heriot-Watt experiment proved that two realities can coexist. It proved that facts can be true for one observer, and different facts can be true for another observer, and both can be correct. It proved that the unity of reality, the singleness of truth, the objectivity of facts, these are not features of the universe. They are assumptions we made, and the assumptions are experimentally falsified. Nobody can explain how to live with this result. The physicists who produced it are still struggling with the implications. The philosophers who study it are still debating what it means. The public mostly does not know it happened. But it happened. The data is there. 5 standard deviations, published in Science Advances, replicated and extended in subsequent experiments, recognized by the Ehrenfest Award as foundational work that forces us to make hard choices about quantum reality. The choice has been forced. We can no longer assume that observer-independent facts exist. We must either explain how they can fail or accept that they do fail. The explanations that preserve them require sacrificing locality or freedom of choice. And those sacrifices are too high. The acceptance that they fail requires reimagining what reality is, and we do not know how to do that yet. But not knowing how is not the same as not knowing that. We know that observer-independent facts fail. We do not know how to build a picture of reality without them. The how will come eventually. The that is already here. In 1961, Eugene Wigner published a thought experiment in the Book of Partly Baked Ideas. He asked what happens when one observer measures a quantum system while another observer watches. He concluded that consciousness must be special, must collapse wave functions, must play a role in physics that inanimate objects do not play. He was wrong about the conclusion, but he was right about the question. The question turned out to be deeper than he knew. It took 60 years to figure out how to test it. When the test was run, it showed that the problem was not about consciousness. The problem was about facts. Facts are not what we thought they were. Wigner died in 1995, still convinced that quantum mechanics needed revision. In a sense, he was right about that too. Not that the equations are wrong, the equations are spectacularly correct, but the interpretation, the understanding of what the equations mean, that needed revision. It is being revised now. The revision is not complete. It may never be complete in the sense of reaching a single accepted answer. But the old picture, the picture of one objective reality that all observers share, that picture is over. The experiments have ruled it out. What remains is stranger than anything Wigner imagined, not a universe where consciousness plays a special role, a universe where facts play a relational role, where your facts are yours and my facts are mine, and the laws of physics do not require agreement. We do not know how to live in such a universe, but according to the experiments, we already do. The universe does not wait for us to understand it. The universe does not pause while we catch up. The facts are what they are. The experiments show what they show. And what they show is that the comfortable assumption, the assumption that reality is one thing we all share, the assumption that facts are observer independent, that assumption is not supported by the data. You can ignore this. Most people do. Most people will never hear about the Proietti experiment. Most people will go on assuming that when they look at the world, they see the same world that everyone else sees. That assumption will work fine in practice. Decoherence will keep doing its job. The macroscopic world will continue to seem objective. But underneath, at the foundations, the objectivity is not there. The foundations are relational. The foundations are perspectival. The foundations are different from what we thought they were. And now you know.